during whatever time I have, I'm going to show you some code first. And the idea there is to give you a concrete sense of what it means to write some scripts using specifically opctv. Then, well, I guess I want to make sure that you understand it's an open session, so just interrupt and ask a question if you have something that either interests you or confuses you, yeah? Or you just want to make a comment, that's fine. So it's an open session. So, yeah, so we'll start with some code, then talk a little bit about MuSig and adapters in the Taproot context. So this is the kind of thing that might be interesting to people who are like coders in this space. Because there's some interesting little details about coding with that combination of features. And then I'll probably also talk about the things. Is that working, or is there a problem, or why is it? I thought he was loading the PDF, and he's apparently not loading the PDF, and I don't have my glasses. Okay. Sorry, I thought you were loading the PDF, yeah? So it should be in the schedule section, yeah? Oh, you're getting that set up, I see. Yeah, So I guess I could start by just saying if there was anything in the original talk that, you know, a question you had, like something that wasn't clear, please feel free to ask that now. It might be a good starting point. Why? What? Okay. Yeah, you need the schedule. Does anyone... I thought it was just in... Does anyone have the URL for the schedule? Because /talks, is it? talks.adoptingbitcoin.org. Thank you, OpenOms, very much. Yeah, no questions? No any... All right, so, yes.
I'm still not clear how you can avoid the double spending.
How can you avoid the double spending problem? Yeah, so the simple answer is .org, not .com, yeah. The simple answer is you avoid it by predefining spending paths. And I think obviously that's terrible, right? Because that's why, I don't know if you remember, I had this weird table with lots of numbers and I put optionality 1, like it should probably be 0, right? It's not really 0, but the idea there is that there are various proposals that involve, I mean, there's things like coin pools, right? Where people are coming up with ideas about how you could sort of unilaterally be able to move money without worrying about double spending. And, you know, the problem is if, a simple example, there's 5 people and we all want to be able to pay each other. How many different ways are there that a set of 5 people could pay each other? That's actually a question. I'm not just saying it. Yeah, which is another fancy way of saying like how many different combinations or different orderings of a list of 5 items are there? Yeah, 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 exactly. It's factorial, right? Yeah, it's 120, I think, but whatever. It's a number. It's large, and do you know roughly how large that number is if it's 10? It's not infinite, no. Luckily. But it might as well be infinite, right? Which is your point, I suppose, right? Yeah. No, it's about 3.5 million. And the general, thank you very much. The general point there is that it's, as you say correctly, factorial, which is basically exponential. It kind of looks even worse than exponential to begin with, but for the mathematicians in the audience, you can use Stirling's approximation to show it's in the limit exponential. What's my point? Oh yeah, my point. There was a point to all that. The point was, the answer to your question is, yes, that's a very severe limitation, because even if you're smart and you predefine every possible path, then it rapidly becomes impractical, right? So the question is, do constructions that have fixed paths in advance actually have any use? I think it's debatable. I think you might find use cases with fixed paths. I wanted to, it's not going to be, it's not too bad. Maybe you can read it. Give an example of what it looks like. So one of the constructions, unfortunately I didn't have a chance to go into every detail, but one of the constructions I called it CTLC, and the idea was, okay, what happens if you just want the simplest construction to be either I get the money after a timeout or it goes into another transaction and it can't go anywhere else except that transaction. That would be either, I think I showed the actual script in the main presentation, didn't I? But it would be, a pointer would be great. Either a script which has, actually this is even more confusing than it needs to be. I shouldn't have shown both the if and else block here because that's going to make you think it's the if and else in the script, but it isn't. Just look in the if block, okay? It says op if block height, op check lock time verify, so that's checking the time. And then to a particular pub key, you need to sign it. The alternative in that script is a CTV hash, which we'll talk about in a minute, op check template verify, which is this newly proposed, it's not new, a proposal, or BIP 119, if you like looking up BIPs, defines this opcode. And something, because I was so rushed, I didn't explain it in the presentation, was when I gave the coin to Oscar and we were doing a real transaction, he was actually broadcasting that on a real network. Are you guys aware of that CTV is active on Inquisition, right? So if you're running Bitcoin Inquisition, but I think another way, that's probably the right way to say it technically, but you could also say it's kind of active on Signet because they're checking the check template verify rules on Signet. So anyway, blah, blah, blah. I don't know if that really matters, but just to mention that if you are doing experiments, and after all, I'm talking about doing experiments here, and you want to try weird transactions using CTV, you can actually do that today on Signet and using Bitcoin Inquisition specifically. I didn't actually look all this up carefully. Can anybody in the room remind me or tell me which other features are in Inquisition currently? So they do have, so that's BIP 118 specifically, yeah? You think so, yeah? Yeah, I think it's, yeah, but I think you're supposed to call it any prev out nowadays, Peter, aren't you? It's just old school, those, yeah. Sig hash replay vulnerable, as Greg liked to call it back in the day. Anyway, we're getting nerdy. But that's the purpose of this session. Apologize in advance. We are going to get nerdy. Yeah, I'm sorry, that's not very helpful. But it is at least worth mentioning, you know, what does it concretely mean when it means you're going to like choose an if-else branch, or maybe you're going to use taproot leaves, I don't know, and you're going to provide a signature. If you're going to the backout clause after a timeout, you're going to provide a signature on the Alice pub key, the A pub key, or if you're going to use the check template verify clause, how are you going to fulfill that clause? What's going to go into that? I'm sorry, I don't have a pointer. The CTV hash there, okay, it's a hash. It says it's a hash, but what is it a hash of? Why am I doing this? Is this actually going to help? No, not really. That's about the taproot part. Oh, there it is, yeah. That's what it's going to be a hash of. Yeah, so I actually cribbed this from James O'Byrne, but it's in the BIP anyway. It's like this is exactly what you hash, right? You hash basically everything in the transaction except for the inputs. And even then I have to qualify that because you can see that it hashes the sequence numbers of the inputs, and it also hashes the number of inputs and the number of inputs, that's the length of the VIN of the transaction, and it also hashes the index of this input. So it basically tries to hash absolutely everything except one thing. Well, what do we mean by inputs? I mean like the previous out point. Well, I always get confused with these different terms. Prev out, the TX ID of the previous, blah, 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 yeah, right. The thing that the slot in. No, but it doesn't hash the actual. Mm-hmm. The TX ID :n if you use that that serialization. You know, a particular TX ID and a particular output. Why doesn't it hash that into?
Importantly, it also doesn't actually hash the script, the spending script.
Right, the spending script, the whole thing. Yeah, good point. Not just the actual TXID in, but also the spending script of the pre. So Brandon is now going to explain to us.
Yeah, so it doesn't hash the script you're spending from, which is normally hashed as well. And the reason it doesn't do this is because it prevents a hash cycle from occurring if you try to lock with a locking script containing this hash. Because if you lock with a locking script containing this hash, and then you try to hash that script, you're in a loop forever.
I guess unless you can find a hash cycle, right? Right, Peter? I don't know. But no, that's just, yeah, I'm sorry, this is a very nerdy discussion. I'm not quite sure where we're going with this. I think my reason for making little screenshots of code, I mean, what does it really do? I just wanted for those people who are curious, what does it even mean to like code something using opctv? And it was new to me, so this was my little experiment of trying it out, right? So yeah, and also to mention, how does this all fit in with Taproot and MuSig, right? So depending on the exact, what I'm calling CTLC construction or PathCoin construction, whatever, depending on exactly which one, we might be using MuSig. So could you put your hand up if you've never heard of MuSig? Okay, so MuSig is, okay, but you have heard of multisig, right? Okay, so the question is, what's the difference between MuSig and multisig? Anyone would like to try? I prefer this to be a discussion because, I can stand here and talk rubbish all day. Yeah, go on, Peter.
MuSig is multisig, where rather than just put the keys into the script, the parties do a bunch of math to create a new key that's based on those keys.
Single key containing
Single key, yeah.
Yeah, they sometimes call it like aggregated signing, or so there's various different terms for it, but just basically it's really cool if instead of printing, we three get together and do a multi-sig, and instead of having to print out all of our keys, we just got one key that looks like any other key on the blockchain. One of the really attractive features of MuSig, which comes out of the Schnorr signature scheme, which was included in Bitcoin with the Taproot soft fork. How long ago? I forgot. But when I can't. That's the bot. I can't remember. 2.25 years ago. Wow, specific. Let's just say 2 years ago. So when we started having Taproot, we created immediately the possibility, although at that point it was, and even now it's very little used, to make these MuSig outputs where more than one person gets together and makes a key that just looks like any other normal single sig key. And not only is it cool, okay, so if you actually want to use MuSig in the real world today on mainnet indeed or on Signet or anywhere else, and you have a number of different ways. I've just realized this is the exact opposite. This is actually a script path spending. But what you can do is you can do that, and then you can make the key be. There's two different ways you can approach it. If you just want to spend only using that multisig feature in the form of MuSig, then you can make the script part of Taproot be essentially kind of nothing, and provably a script that you can't spend. It's very easy to do that. The opposite is what I'm actually showing here. I'm sorry, I forgot. This is the exact opposit. Sometimes you'll want the opposite thing. You want to be able to prove that this Taproot output, this Taproot address that we're using, is only spendable using a certain script, such as a complicated script like the one I just showed you there. Some complicated script like that, and then you want to say, well, yeah, we want the spending to be using that script, but we don't want to have an overall what they call internal key that allows spending by just a pure signature. In that case, you're doing the opposite thing, and you have something called, well, it's a concept that nums, that you might want to create a public key that nobody knows the private key to. I don't know if that's a familiar concept to most people here, but that's really nice because it means, like what I'm doing right here is creating a Taproot output or a Taproot script pub key, let's say, that can only be spent with a specific script and can't be spent by a collaborative signing event. So there's two, I don't know, I completely confused that description, but there's two different things we're talking about here, right? One of them is MuSig, and one of them is paying with scripts. What's this? Oh, we all did that. And so maybe we'll just spend like 5 minutes on, I know it's very technical. Some people will love this, but I guess most people will find it a bit weird. More drilling in a bit more detail about this whole MuSig thing. So in normal multi-sig, you know, there's three people. There's Alice, Bob, Carol, and each one of them provides a signature, right? And in the old days of Bitcoin, that's how it worked. And you used to publish those three signatures on the blockchain, and you had the weird rules about that. So how it works with MuSig is rather different. What you do is each person makes a signature term, like it's literally a 32-byte number, or 256-bit number, using a formula. Let's just say that's a formula. And then there's a complicated decision about how do we make the nonce. Does anyone here not know the term nonce in digital signature? Nonce? Okay, so nonce is basically, it literally means number used once, but whenever you spend a Bitcoin transaction, you have to give a signature, agreed? You have to sign it. That signature isn't just a signature. It's a signature number plus another number, which is a special number that you only use once for that signature, which kind of helps to keep your private key secret. So you have to produce this nonce thing every time you sign. Let me put it like that. You'll often see it written as R in these equations as being the nonce. And the problem is in the MuSig constructions, they're much more difficult and complicated to decide what the nonce should be. So you have to have some weird negotiation process or some advanced mathematics to form a nonce that is actually safe. Because all of us are sort of cooperatively producing the signature, it adds extra security issues around that. In this particular, well, in the code base that you'll see linked on my presentation, and here, I'm talking about how MuSig 1 works. There are two versions of MuSig. In MuSig 1, you'll just kind of commit to the nonce in advance and then produce the nonce after having committed to it. The benefit of that being that nobody can adversarially choose their nonce after having seen your nonce. That's the basic idea, and it's, in my opinion, the easier way to understand MuSig and perhaps to code it, but MuSig 2 is a little bit more advanced. Let's not get into that. The output is the same. Each person produces a number, each person decides on a nonce, and we kind of just add them all together. And because we add them all together, we get one final signature and one final nonce which appears on the blockchain. And it looks just like the same, it looks just the same as the nonce and signature that you would get if you did a single signing on your own. So that's a very beautiful property, but it was achieved, believe me, after an enormous amount of hand-wringing and technical calculations and proofs. Literally, I think it was like 4 years of research that eventually resulted in a safe way of doing this.
What you're saying
Yes.
it looks like it just came from one.
Yeah, it's not exactly. It's the entire purpose of all that research and this output was to achieve that goal. Probably more than anything. I guess you could say scalability as well, but the fact that it's not distinguishable is a very beautiful property that we were really focused on. And another beautiful property, which is a kind of a side property, is what's called adapters. And what adapters achieve is the idea that you have the option before publishing your partial signature. So this quantity here, sigma I being the index, perhaps 1 or 0 or something. Before publishing that, you can publish something else, which you call an adapter signature, which proves that when this is revealed, this will also be revealed. And that part is barely even high school mathematics, right? Because if you look at this equation, if I give you that, and then later on you see that, clearly you can find that, right? So that part at least is pretty easy. So by sharing adapter signatures with each other, we can create a situation where when the transaction finally appears on the blockchain, albeit it's quite complicated, you can extract the secret data. And you know that you will be able to extract it when the transaction is published. I'm giving you like the really short version of adapters there. I mean, this is... Ask questions if anything is not, or if everything is not clear. Ask questions. Okay, let me ask you some sort of prompting questions. Has anyone here, put your hand up if you've heard of PTLC. That's most people here. Okay, open arms. What's PTLC?
So the point signifies like a point on the elliptic curve.
Yep.
So it is not tied to a specific signature, but it can be or a specific hash, but it can be a pointage. Then it's or done a bit more freely than just this hash.
Yeah, it can be changed. It's kind of it's the linearity. The big difference between this kind of construction and hashes is this. If I take the hash of the number 1 and I add it to the hash of the number 2, I don't get the hash of the number 3. And of course, that's it. I'm sorry, we were 15 minutes late in starting. We were 15 minutes late in starting. I'm just explaining why I'm going to be a little bit late. I'll try and cut it down, but I was 15 minutes late in starting. So you might not want to hear that. But okay, I don't know. Honestly, this could be like an hour-and-a-half presentation on its own. So I don't know whether we should go into it in detail. But the linearity means that we can combine. It's precisely why this whole thing works in a signature, is because of that linearity. We call it linearity. It just means that if I take the public key of 1 and add it to the public key corresponding to 2, I get the public key corresponding to 3, which is basically what we're doing here with this little quantity t. Is think of it as like a private key and there's a corresponding part. Okay, I obviously, because I was started so late, I'm not going to be able to do what I wanted, but I do at least want to talk about yeah. So that gives you a little bit of background on MuSig and adapter signatures. And what I called private PathCoin, in some ways it might be the more interesting of the ideas that I presented. I didn't really present it, I didn't have time. But you could make multiple MuSig signing sessions on the same coin, on the same UTXO, let's say. Let's say it's 5 of 5 for argument's sake. Each one of those signing sessions would pay out of that UTXO to a different, let's say to a different address, owned by the different parties. And obviously they conflict with each other. If we sign all of those 5 of 5 signings, we're going to have 5 valid signatures to pay out to 5 different places. Well, that's not much use because then we don't know who it really belongs to. So the concept was in there. Where's the picture with the, why am I going backwards? It's always good to go forwards. There it is. The concept was that, for example, look at the first row. Alice might be given, so Alice, the first one, A, might be given signatures from B, C, D, and E. That would allow Alice to spend the coin. But before Alice has handed over these signatures, so that's kind of the wrong picture, maybe. Is there an earlier one? No. So before Alice has handed over these 4, then she can spend it, but nobody else can. If she wants to give it to Bob, she can give her signature to Bob, and you get 4 out of 5, and again, Bob will be in a situation where he can spend it, but then there's a conflict where both Bob can spend it and Alice can spend it, in the same way as if Alice handed over her private key to Bob, that would be a conflict. You wouldn't actually transferred money. So the idea would be that there should be some kind of penalty where Alice will suffer some penalty if she illegally spends the red cross there. If she actually publishes Sigma A1 on the blockchain via a MuSig signature, she should suffer some penalty. So the way to achieve that would be to have an actual penalty or fidelity bond output, which itself was tied to an adapter signature. So the idea is Alice would give Bob an adapter signature, as well as some other details that I won't get into, such that if Alice broadcasts that first signing session to her own output address, Bob will be able to claim a penalty which is greater than the actual value of the coin. Is that making any sense? I don't want to spend too much time because I know there's people waiting, but does that make any sense to people? Or?
Yes, that makes sense. I have a question.
Yes, you have a question, right? Thank you. Save me.
So now that we have this fidelity bond, with this fidelity bond, does that mean that each party to this has to have their own fidelity bond?
Yeah. Yeah, so the only, in itself it isn't a very interesting observation, I would say, but I think the only interesting observation is that if the penalty bond has the structure of what I called CTLC before, in other words, this structure, it at least achieves this goal, which is that each party will only have to put up, that structure, only have to put up an amount equivalent to the coin itself, not to n times the amount, because the problem is if you just do it naively where each person pays a penalty to the next person, you have the problem of collusion, because there's a lot of people involved. So you always have to assume that everyone else is colluding against you, right? That's the default assumption. And in that case, the only way to ensure that if you were cheated, that you would get paid would be if every penalty paid out to every other person the amount of the coin, which is really bad. It's already bad, but that would be really bad. But if you use this kind of construction, then you can, as you pass the coin from one person to the other, you don't only pass an adapter signature. The adapter would feature here somewhere. You'd also pass another locking secret, which would allow the coin to move to the next person, to the correct owner on the path. So the answer to your question is yes, every person who spends the thing needs to put up a penalty bond. If you only receive it and then you broadcast it, then nobody cares, right? But every person needs one, but they only need the amount of the size of the coin, not amount of the coin times the number of participants. I think honestly that's the only really interesting observation here. Whether that actually leads to something that's even remotely practical, I don't know. But I will let you ask any further questions. But I was started 15 minutes late, as a lot of you know. So I feel under pressure to stop really. Any questions about anything? No? Yeah. Go on.
Starting with explaining the size limitations, so really we are talking about 10 participants are getting to be like.
Well, it depends what you try to do, right? I mean, there's a number of different. Yeah, you guys, I was started 15 minutes late. That's why. Sorry, I don't want to stop saying it. I just mentally I can't handle it. The thing is, yeah, absolutely. If you wanted to build like a tree of all possible spending paths, absolutely. So actually, maybe there is one final slide I probably should show that I didn't have time to, which was, yeah. So I thought a lot about that. I didn't really come to any really solid conclusions. Clearly, you could build something where everyone can pay everyone else as long as the number is something less than 10. And clearly, if it's big, you can't. It's just completely impractical, even if it's theoretically possible. So how could you ameliorate that? I mean, you could find, it depends how restrictive you want to be to yourself. Because if you remember from my original talk, I was trying to get across the idea that you could pay money by just handing over a USB stick. That was like my main goal. So yeah, I can dream up designs, and many other people have dreamed up designs. I mean, obviously, coin pools really comes to mind here, where you've got a lot of people getting together, and they can transfer coins in an off-chain way, as long as they keep collaborating with each other. They have to keep signing new state updates all the time, right? So I'm looking for, is there a way to avoid that? And I'm not sure that there are any really obvious ways, but you can maybe jump steps, depending on how you look at it, because maybe, for example, if Alice wants to pay Carol, Bob could have a program somewhere that just hands over essentially the necessary secret data. Because Bob never owned the coin, you could argue that Bob will be happy to run that as a kind of a, in quotes, watchtower type thing, where it's really, really easy to do that. In theory, I don't know. Maybe if you start including stuff like any prevout, which has slightly different properties to this, although there's some overlap, it might be the case you can create, I don't know, situations where the coin ends up going back into the state it started with, or something like that. It's pretty tricky to figure that out. I mean, I haven't figured it out. But your basic observation is absolutely correct, that you can't create scenarios if everyone can pay anyone at any time, because combinatorially it's just not feasible. Yeah.
You have to predefine everything from the start.
Essentially, yeah, and I think somebody mentioned that earlier on, is that that's the sort of main limitation of these kinds of designs, is that you have to, I mean, one possible scenario that is interesting is two people. In a way, just go back to the simplest case, because a Lightning channel is two people swapping money between each other. If you limit it to them swapping the entirety of the UTXO between each other, they can kind of do it cold like this. They can kind of do it offline. I've seen a couple of different designs like this. Like even just pre-signed transactions gives you a lot of that without covenants. But that has slight trade-offs as well, which I was kind of looking at it this morning. It's really interesting, actually, but I don't know.
I think
Yeah.
what's interesting here is with the adapters,
Yeah. Yes, that
you
idea.
have a bunch of separate adapters.
Yeah.
Then that you can extend how many times the thing can go back and forth between the same two parties. Potentially, you have two
You mean
parties
there's a bunch of different adapters on the same signature, or?
on the. So you have, each MuSig session
Yeah.
has a separate
Well, yeah, it does, yeah.
adapter associated with it.
Yep.
Which penalizes to the right person.
Yeah.
But if the penalty could be spent by several different adapters. So you set up a penalty
Right.
with many different
But then, as soon as a penalty is spendable in multiple different contexts, you have a collusion problem, right? Because
Well,
yeah.
It's a two-party question. So if you want
Right, the two, yeah.
You make a bunch of separate adapters.
Yeah.
And swap the coin back and forth.
Oh, for sure, yeah.
Somewhat indefinitely.
Yeah, absolutely. There's a few designs like that, for sure. And it brings to mind a really strong thing I'm seeing from looking at this is the thing that Covenants changes is, I think, well, the main thing it changes is you remove the collusion problem of having n instead of 2, right? Well, it's not the only thing, but two-party systems, they have this intrinsic advantage because there's only one person that could possibly be penalized, right? But when you have n people, there's a lot of problems. Anyway, I think I should stop there because, it's only fair that people need to get on with their lives. So thank you for coming, and please feel free to ask me questions offline.